Thanks for the organizers and the scientific committee for the invitation to this workshop. I think every set theorist should give one talk at least at the Young Set Theory meeting in order to have to see that there is future and to enjoy this fact that it's encouraging to see this audience. Okay, I'm going to talk about what is written in the title, but I'm going to try to make it accessible. And if there is something that I don't think there is point to get into details, I will not. So don't bother yourself too much. If there is something you don't understand, just go on, proceed. It's I try to focus on what looks more like set theory than the other part. Yes, I will present at the end, so there is reason to wait, two problems which are very simple to state, and well, they are to a large extent they are still open. One of them is just embarrassingly open. Those of you who follow Math Overflow already know about it, but maybe the others. Yes, so I will talk about this. Let me just start and see what happens. Okay, we will talk about topological groups. Moreover, we will talk only about a billion groups, a billion topological groups, which is simpler, even though the results extend also to non-abelian, the specific results that we will talk here. A billion is easier to understand. What does it mean to be a topological group? It means that the group operations are continuous. Just that. The group operations are continuous. There is a topology on the group, and like the Bar-Ilan with ordinary topology, or just any. You can take any group and put on it the discrete topology, so everything is continuous. Or one-dimensional torus, which is just the quotient of these two. So it's convenient to view it like the unit interval, and when you add and there is an overflow, you just subtract one to go back to the circle. So it's sort of it's a circle group. You identify y1 and 0 in this group. Okay, why bother talking about discrete topological groups? This is just group theory, not topological group theory, but it is still important. We will see. Okay. So every topological group is, because of the continuity of translation, every topological group is homogeneous. This means that locally at every point the topology looks the same. Why? Because you can shift any point to any other point by adding an element, just by translation. So if this is the group and this is the identity element, for example, you can map it to every element x, or let's denote it 0, by just plus x. And this is a homeomorphism, so it looks the same. Therefore, it suffices to study neighborhood bases at the identity element. If you know what happens, how the topology looks at the identity, to a large extent you know what happens in all of the group. Locally, at least, you know everywhere what happens because of homogeneity. The most important cardinal invariant of a topological group is chi of g, the minimal cardinality of a neighborhood base at 0. So you want enough open sets around 0 such that every open set I give you, there will be someone. I give you any open set, there will be in my family some neighborhood which is smaller than that. This is just the cofinality of the neighborhoods of 0. And of course, because this is the most important thing, how the neighborhoods at 0 look like, then this is the most important cardinal invariant of a topological group. Here are some examples. If you take the Bar-Ilan, then it's enough to take countably many neighborhoods of 0, minus 1 over n, 1 over n intervals. The discrete groups, you just take one, the singleton, and it's fine. This is the character. One reason why this is important is that a topological group is metrizable if and only if it has a countable neighborhood base at the identity. Its character is at most aleph 0. These are the examples here. You see that the character is at most aleph 0, and they are, of course, metrizable groups. Yes, in fact, this is an important theorem, but one can prove it on his own with enough thought. I mean, it's not such a big thing to do it, to prove it, but it's beautiful. Okay, so we will talk about the free abelian group. What is that? It was introduced by Markov long ago. It's denoted A of x. So x is a topological space with some separation hypothesis like Tikhonov. It should be nice, but topological space. And then you think about the elements of x as elements of a group with no relations among them, sort of a basis, like in linear algebra. No relations among the x's, but you can add them. You can add x1 to x2. So what you take is all linear combinations over the integers of elements of x. These xi's, they come from x. These are the elements of the group. So you see the group, this is just the abelian group generated by the elements, the points of x, of the space x, with no relations, except that it is abelian. This is why you get these coefficients. What is the topology? So algebraically, this is very clear what is this group. Topologically, it's much more complicated and much less understood, this group. So I didn't say what is the topology. The simplest way, perhaps, to define the topology is a categorical way, is this, that what happens is like in linear algebra, if you take a basis for a vector space, linear space, then you can extend every function on the basis to a linear function on the span, on the space, on the all of the space. So the same thing here. For each continuous, okay, H, the definition is as follows. For each abelian topological group H, and for each function, just function, a continuous function, sorry, this is a topological space. So for each continuous function phi from x to h, so you can assign continuously to the point of x any point of h as you wish, just it should be continuous, this assignment. There is a unique extension into A of x, which is a group group homomorphism, so that it respects addition and negation. There is a unique. So every function on x extends to a homomorphism on A of x. There is a unique topological group which has this property, and it is denoted A of x. This tells you not much about the topology, but that's the shortest definition. There are explicit definitions that are much longer, much more complicated. Yes, okay. So the first question about the topological group is, what is its character? What is the minimal cardinality of a neighborhood basis at a point, at 0? That's the question. The goal, well, you see, X could be any topological space. So you cannot answer, the answer is aleph 2, okay? You cannot say that. But the goal is to find the character in terms of properties of X. Some cardinal invariant of X, ideally, some cardinal invariant of X will determine the character of A of X. This is ideally the goal. So X is it's a given topological space. You can look at it and determine essentially determine any cardinal invariant you want. And then you go to an object which is quite obscure, and you can tell what is its character. You can tell something about it. You can pull properties from X to the more complicated A of X. This is the ideology of this approach. In general, that's what you do. You try to reduce a difficult problem to an easy one. So we will talk about that. Of course, the character is just a cofinality. Let us look at one more cofinality, already defined today by Meggio, the dominating number. You can take here always, you can take here eventually. It's the same. You get the same cardinal for D. You don't here. Yes, and not much is known. I mean, everything here is consistent. You can make D any cardinal between aleph 1 and the continuum. Only you should know that the cofinality of D is uncountable. That's true. And this is another, we talked about invariance of a topological space. So the weight of a topological space is the minimal cardinality of a basis for the topology of X. How many open sets you need to generate the topology? So this is a special case, but still important, of the main theorem that I'm going to, the main theorem of the paper I'm talking about. The dating is maybe not precise. It was anticipated, then it was published later, but it is published. Okay, so we consider spaces which are particularly nice, but still quite general from this point of view of the free abelian topological groups. These are spaces such that there is a countable cofinal family of compact sets, which, moreover, determines the topology of X. This means that a set is closed if and only if its intersection with all these compacts is closed. So it's not so important to understand what it means, but let's just think intuitively. Such a space is called K omega. It's a nice space, a special case of a sigma compact, let's say, a countable union of compact sets. Here it's actually a cofinal family of compact sets and something more. Anyway, we take this for granted, and this is just an example. If you take the direct disjoint union of compact sets, not these ones, just any compact sets, then it's an example of a space which has these properties. Okay, so if there are such Kns, you can look at the weights of them as topological spaces and take the supremum. Let's call it kappa. So this is a cardinal invariant of X. It's a property of X. This kappa is determined by X. And I claim, the theorem tells that this kappa, this property of X, determines the character of A of X, of the free abelian group. This is the point. This is the theorem. The character of the free abelian group is the maximum of D, the dominating number, and this very familiar from PCF theory function, cofinality of the countable subsets of kappa. So in particular, X, this cardinal invariant determines the character of A of X. So the rest is like this reduces the question to set theories. Now you can ask yourself, what are these numbers, etc. But this is pure set theory. There is no more topology here. This is just set theory. Okay, some example. You take the real-line. Then here you can take the real-line is an increasing union of a compact set, just closed interval, countable union. So the real-line is good for us. And then the character is just you plug in here in this kappa. The weights are just aleph 0. So this is 1, this number. It's funny. You never plug in aleph 0 here, but here you do. You get 1, but this is D. Okay. Yes?
Obviously, this kappa doesn't depend on a particular choice
of the Kn. Well, it's cofinal, so probably you can somehow sandwich, every compact you can get a compact set in this family, but also vice versa. So, and the weight is monotone in the proper direction. It should be okay. Okay, and previously some special cases were known, and this is a generalization. Like when X is just compact, so just X, all Kn are just single K, X is just K. So it was known before. Exactly this equality was known. But using elementary methods, and very difficult, we will use non-elementary methods. I now give an introduction to this theory, very nice theory, one of the greatest achievements of mathematics of all time. Not mine, okay. Due to mainly Pontryagin, but Van Kampen actually generalized it to the correct setting. So we identify the torus with this interval by just shifting it to the left. This is more convenient for our purposes. And we talk, when given a topological group, we can look at the set of all continuous homomorphisms from the group to the circle group, to the torus, okay, to the circle group. These are called characters. It's funny because We said before that the character of a topological group is something, and now we talk about characters of topology. This is not the same thing, but this because these two notions came from different fields, and they are now connected by this method. So it's just a collision of terminology, birthday paradox, if you want. Okay, so you take the set of all continuous homomorphisms, and this is very nice. Think about logic. What is a truth table? I saw it in Halmosh, I think. A truth table is a way to analyze a complicated logical object by looking at all relevant functions from this object to the simplest logical object, which is true or false, just two-element Boolean. So you do it in many places in mathematics. You take the simplest possible topological group, essentially, which is not trivial. So this is the circle group, and you look at all continuous homomorphisms. And if you are, this is like the truth assignments in this analogy. If you can say something about them, maybe you can learn something about the group itself. That's the approach. Now, this is a group with pointwise addition. You can add the two characters, phi1 plus phi2 pointwise. So that's a topological group. And the topology of this group, I didn't say, but the topology is the compact open. So you look at all characters that do not stretch, that somehow put all of the compact set into a small interval around 0. This is a basic neighborhood, a closed neighborhood, but a neighborhood at the identity. And this provides a neighborhood base by definition. This is the definition of just the compact open topology. Some examples. Let us look at them a little. The dual of the integers is the torus group. Why? Because you look at when you look at the character from the integers into the torus, into here or here if you want, if you know where the element 1, which generates z, goes, you know where every element goes because it's a homomorphism. So actually you only need to know the image of the generator, and then these alphas, they just constitute together the torus itself, the circle group. You can similarly observe that the dual group of the real line is the real line itself, so it's reflexive in a sense. Okay, so the analogy with linear algebra continues here. You probably learned at first year linear algebra, you have the vector space, and then it's star, and it's double star, and then the double star turns out to be the same in finite dimension. So the same thing you hope to have here, not in the most general, but you ask when this is the case. You can take the dual and then the B-dual group. There is a way to get from the group itself to the B-dual without going through the dual. And it's very simple. You want somehow to think about elements of G as if they belong here. So this means they should be homomorphisms on G hat. Okay? So every element of G should act on an element of G hat, which is a homomorphism. How do you act with a point on a function? You apply the function to the point. That's always you do it this way. So we say that G is reflexive. That's a definition. It's not always the case. G is reflexive if this evaluation homomorphism, this homomorphism is in fact an isomorphism. So this is the big theorem of Pontryagin and Van Kampen. Every compact and every discrete topological group is reflexive. It is isomorphic via this simple natural embedding. It's isomorphic to its bidual. And this was generalized by Van Kampen that every locally compact topological group is reflexive. That's as far as the classic theory goes. Yes. So probably if you put the real line, you will get something a little different. I don't know exactly. There are some differences. Sometimes they are not so important. It depends what are the questions that you ask, etc. For this is like turns out to be the correct object. It's compact to start with. It's good that it's compact. It's useful. Okay. Well, there is. the point is somehow, if you start with a compact group, you move the dual is discrete, and vice versa. If you start with discrete, you get compact. So the idea is that you can start to study topological groups, the general idea, by looking at their dual. Here we do something different, but if you look at their dual, you get just groups which are discrete with no topology. So you sort of can apply group theory to study topological group, and vice versa maybe. And there are some nice connections. Some elementary properties of topological groups translate to elementary properties of groups, discrete groups, standard group theory, and vice versa. Okay, subreflexive groups. So most groups are not locally compact, so the classic theorems do not apply to them. Even if you take a metrizable, a metric group, so nice, you take its dual, it's not necessarily reflexive, so not necessarily the same as the bidual via this embedding. So let us say that a group is subreflexive if it's isomorphic to its image, just isomorphic to its image, but maybe the image is smaller than the bidual. This is, I call it subreflexive, and like a picture, you have the discrete groups, you have the compact groups. All of these are locally compact groups, but there are many more subreflexive groups. So, yes, for example, duals of metrizable groups are subreflexive. Okay. Some pictures are generic. You can use them for any lecture. Yeah. Okay. So let us survey the proof steps to get some idea. Why to do this? I need to find an answer. I think the reason is this is a young set theory workshop, and somehow to see that it is sometimes possible to actually apply our methods to outside of set theory, and I think it's very important. I would like, as much as possible, to encourage you to try this, to talk to people who have questions that feel close enough to set theory, that if you talk to them long enough, you will meet somewhere in the middle. And this is what happened in this project. For several years, it took us to reach the middle point and actually get a full argument and insight, some insight. It's very nice and very important, I think. It's important to develop set theory. And I think, personally, it's equally important to apply set theory beyond set theory. For example, to topology, that's the closest, but maybe to other things, algebra, Banach spaces, you probably know, etc. Okay, so our assumption on the group that is it's a group nice with cofinal family of compact sets. Sorry. Yeah. So first of all, we are in good starting position because it is known that A of x is subreflexive, in this context at least. That's great. When a group is subreflexive, it means that you can, its topology is inherited from the topology of the bidual, and we will see how this could help you. Here, okay, in fact, we already see. If G is subreflexive, then its character is equal to the cofinality of the compact subsets of the dual group. Compact subsets of the dual group, just compact sets, you take the cofinality. This is already a standard set theoretic object. The compact subsets of a space, you take the cofinality of that. So this is, if you make the neighborhood smaller, then the compact set gets larger. I think it's like anti-monotone. If you increase the compact set, you make it bigger, and you want to send it to a small interval, it's harder. So the set of characters becomes smaller. Sort of. It's, in fact, there is a picture here that, not a picture, but a diagram that will show this. To notice this, one looks at a standard operation called polar. The polar of a set is the set of all characters. Maybe I shouldn't use chi, but it's not this chi. It's the set of all continuous homomorphisms, okay? That do not expand A too much. So you have this interval, and everything is sent to minus half half. Okay, so you have some interval here. And you just take a small enough interval. Quarter is just works, but you can take anything smaller than 1/4. And you want that your homomorphism will send all of the points of the set into here, not outside. This is this is the definition of the polar of an arbitrary set. And then there is a sort of connection. When you take a neighborhood of the identity, and you apply polar, you get a compact set. This is sort of a lemma. You need to prove things here, but that's what happens. So the polar of a neighborhood of the identity is compact, and the polar of a compact, by definition, is a neighborhood of the element, because we are in the compact open topology. What is nice here, this object looks strange, but if you intersect it with G, because G is a, okay, you identify G with its image, G becomes a topological subgroup of this. So it's a topological subspace. You can intersect this neighborhood with G, you get a neighborhood of G. You just lie in a bigger space. But so using this basically connection, you obtain this fact. It's not that I claim I did the proof, but it's with this line you can create the proof yourself afterwards if you want. Okay, now one more nice thing is that Pestov proved that the dual of A of x, which is the A of x is what we want to study, is just the set of all continuous functions from x to t with a compact open topology. Just all continuous functions. Cxt is also well-studied object with a compact open topology. What is nice, okay, let's see what happens. Let's summarize. So the character of A of x is equal to the cofinality of the k of the dual, the compact subset of the dual, but the dual is Cxt. So this is a summary. What we want to find is this thing. Maybe it looks more complicated because there are more letters, but the objects are simpler. Why? Because here in X, there are a countable cofinal family of compact sets. And if you look at these neighborhoods, they constitute, because it's a cofinal family, these neighborhoods constitute a neighborhood base at 0, and therefore the group, this is a metrizable group. It's a metrizable group. It's a very simple object. And it has some nice properties. This was proved by Arendt's complete and non-locally compact. So what to do with this? We have a metrizable metric group, which is complete, not locally compact. And we want the cofinality of the compact subsets of this metrizable group. One more nice thing. Its density is stable. By this I mean that if you take any open set, all open sets have the same density, let's say, in this group. The density number means how many points you must take in order to get a dense subset. So all of them have the same density. And this density is exactly the supremum of the weights of this Kn, which are the Kn inside X, this cofinal family. So this is where kappa comes from. It's the density of this group. Okay, nice. This is the summary of the situation. We have a metrizable, complete, not locally compact, a topological group of stable density kappa. So a very nice topological group, gamma, in short. The claim is that in this case, if gamma is like that, then the cofinality of the compact subsets of gamma is equal to the following theoretically defined cofinality. You take all sequences of finite subsets of kappa. Kappa is the stable density of this, the density of this. You take all sequences of finite sets, and you compare by, if you take a larger finite sets, you get something larger. So you have a sequence of finite sets, and you have another one, f1 prime, let's say, f2 prime. Then you say that this is less than or equal to this if pointwise the sets are smaller. Just the natural. The most obvious thing. And this is the claim. So maybe I will say a few words about why this is true. Basically, okay. What happens if a group is metrizable, then we take, in fact, the easy direction. There is a countable neighborhood base at 0. Okay. And you can fix a dense subset of gamma of cardinality kappa, which is, we assume there exists. And then what you can do is map a sequence of finite subsets of D. This is now our set of cardinality kappa. You map it to this intersection. What this tells us? if a set is compact, then for every open set, there are finitely many shifts of the basic open set that will cover it. So for each n, it will be contained in one of these guys. And therefore, it will be contained in such an intersection. And therefore, you will get a cofinal family. If you map a cofinal family here, you will map it here, you will get a cofinal family in compact sets. Well, here you take them to be closed neighborhoods, etc. And then you get totally bounded, and it will be a compact, and then it's OK. But that's the idea, that every compact set is containing finally many translates of U for any given U. That's one direction. Another was much harder to find the correct concepts. You sort of use discretization. You have an open set. You put in it grids which are very, very discrete, far away in sense of the metric from one another. And then you take union of these grids, and it will converge to the density. You take maximal grids, sort of. Just that's the idea. And then what you will do, you will map. OK, you're given a compact set. You will intersect it with the grids. You will get finite sets. And these finite sets, they are not in something like that, but they're in something equivalent. You take the product of finite sets of an, and the cardinalities of the ans, they grow to kappa. They grow to kappa, or maybe always equal to kappa. It depends on the setting, on the situation. There are two cases. In any case, when you have cardinals lambda n going to kappa, then this is cofinally the same as this guy. It's just also not surprising, sort of continuity, set theoretic continuity. So you need to prove that a cofinal, OK, you need to prove that such an element, let's see what I want to say. What I want to say is that if now you take elements like here, OK, OK, basically what happens here is that if you take these finite sets, these sets an, they get smaller and smaller, and then you take their union and add 0, you get a sequence that converges to 0, and then you get a compact set. So you get when you start with an arbitrary element here, you get a compact set here, and this explains why you get a cofinal image. If you start with something cofinal here, sorry, OK, I'll have to figure out for myself, recall what happened there, but that also was a key point, that somehow if you have a sequence of sets converging to 0 and you have finite sets, then the union converges to 0 as well, and therefore with 0 it is compact. Yeah, there are some subtleties here. This is why it's difficult for me to explain, but some ideas maybe you see here, maybe, I hope. So let us take this for granted. That's the proof, that's the sketch, let's say, of the proof. Let us take now this result for granted. So there remains only one final observation. This structure that I just defined, all finite sequences, all sequences of finite sets, its cofinality is the same as this thing, set theoretic object. Why? Because if someone gives me a sequence of finite subsets of kappa, I can take their union. It's a countable set, subset of kappa. So assume I can make it as large as I wish, like what you see here. And then inside the union, I chop it. This is now a countable set. I take finite pieces, but in very, very quick jumps. This is where D comes from. Then I will get a cofinal family of sequences. So this is the way you translate from the left-hand side to the right-hand side and vice versa. That's the point. So you get the theorem, basically. These are the steps of the proof. OK. So set theory. So let us survey for maybe some students here still do not know. So what is the cofinality of this guy, this object of all countable subsets of kappa? So this is just the motivation, is our theorem. Of course, this wasn't the motivation of Shelach, but I mean, for this lecture, why to study this? So of course, Aleph 0 is easy. One subset will be countable. Just take all of Aleph 0. But if you take Aleph 1, you get Aleph 1, and similarly for every Aleph n, by induction you can prove it, actually. for aleph 1, you can prove it and then use induction. And when you go to the limit, it's not so clear. What is the cofinality? This is the first point, aleph omega, where this cofinality is not completely understood, what it is. But there is a big theorem about it. Okay, this is not a big theorem. By Koenig's lemma, this cofinality is greater. So it's not like the previous points. There is a jump. It must be at least aleph omega plus 1. And this is a central object in Shelach's PCF theory. There is an upper bound on it. You open Shelach's archive. You all know this page, right? You Google Shelach, you found it. And this theorem is more or less implicitly an upper bound on this cofinality. Why? Let's recall. Because when you compute aleph omega to the aleph 0, I guess this was, by the way, the motivation for studying this object. When you compute it, you see that it's equal to this thing, right? You need the cardinality of all countable subsets, but you can do it like that. What I wrote here? Just a second. If you take a cofinal family, countable. Here you take just a cofinal, but for each of them, you take all subsets, or all infinite subsets. Then you get all of them, okay? If you take a family of countable sets, and for each of them, you take all of its countable subsets, then you get all of them. So this is equal, the cardinality is equal, and this is, okay, 2 to the aleph 0 times this. And then there is this theorem of Shelach. This is this 2 to the aleph 0. Shelach writes plus, not times. It's the same thing. Yes, okay, so this is the big theorem, actually. What Shelach writes here is this theorem. The cofinality of aleph omega to the aleph 0 is smaller than aleph omega 4. Okay, why 4? It's deeply rooted in the methods, but there is no, it's not clear that this should be optimal. I mean, maybe you can plug in something more natural, a priorily natural, smaller than omega 4. Okay, in general, yes, such a theorem. You take the fourth successor of alpha, and you will get this. So here, this is case of alpha equal omega. You get this theorem. This is true for all alpha smaller than the first fixed point of the aleph function. This is Shelach's theorem. Okay. Consequences of Shelach's theorem. So I don't know, maybe there are in the audience some people who are afraid to study Shelach's PCF theory. I don't know. But one of the mottos of this lecture is you can still use it. I mean, even if you don't know to prove Shelach's theorem, you can still use it, sometimes as a black box. So here are some consequences that just by transfinite induction using Shelach's theorem, you can prove basic things. Of course, they must be known to all experts, but to me they were not known. I'm not an expert, so I had to prove them, but it was easy. Okay. So here is a cute corollary. For every kappa with these properties, so okay, this is because the Shelach's theorem does not talk what happens at beyond the fixed point, this point. But below it, if kappa is like that, for every kappa like that, you have this. The aleph kappa, not kappa, but aleph kappa to the aleph 0 is a fixed point of the PCF function, if I may call it so. But this is nice. So you know what is the character of A of x for all these cases. It's just aleph kappa. Completely. Okay, times d. If d is greater than it is d. So this is an example. For each n, it's actually equal. The example of kappa of this kind, you know, that you can plug it in. So aleph n, why not? Okay, and there are some consistency results. Yeah. So, okay, this is not a consistency result, but if there are no large cardinals somewhere, then in fact this function obtains its minimum possible value, which I love this theorem. It tells that if you somehow think that large cardinals are sort of very, very strong hypothesis, so maybe it's okay not to assume the negation, okay? If you think so, then this function is completely understood and very tame. In fact, the fact that it's very tame is the point in Shelach's theorem, but actually it's, you know what its values. It's kappa when the cofinality is greater, and when it's aleph 0, it cannot be kappa. It must be greater, so it's just kappa plus. So in some sense, this function, or in this sense, it's completely understood. This sense is called, if you assume this, it's basically so-called Shelach's strong hypothesis. It's not strong hypothesis, it is strong compared to something provable in ZFC. But that's the, I mean, this is why he called it strong hypothesis. But yeah, so that's Shelach's strong hypothesis. It's a very weak axiom. Okay. So something about the large cardinals and some further motivation. Okay. So in fact, other studies in topology, if those of you heard about, okay, all of you heard about almost disjoint families in omega, and you can talk to us, you can assign to every almost disjoint family in a canonical way a topological space called psi of this family, psi spaces, or Brovka-Isbell spaces, if you wish. And when you study these spaces, you get into questions of this sort. Is it true, this is due to Bonanzinga and Matveev, is it true that for every cardinal kappa up to the continuum, the cofinality of this object is d times kappa? Now, when they posed the problem, they didn't know that it's d times the PCF cofinality. It's much more convenient to put it. And they put a similar question, in particular for kappa at most d. So here, this is just the maximum will be d. So is it true always that this is the case? And they knew that the answer is true, is yes, for every aleph n, and also for the continuum, for simple reasons. And we know that this is true. So it's basically a question about the PCF function. So it should be easy to solve. So for one, the answer is easy. If d is smaller than kappa and kappa is a countable cofinality, then this will jump and will be greater than d. So this will be at least d times kappa plus, which is kappa plus, because we assume that, and the answer is no. So for one, it is easy. For two, it is you need to work a little more. You ask, is there kappa which is at most d? So what we do, okay, that's the theorem that the answer is no, this is not provable. You assume large cardinals, because as I said before, so you assume, okay, to get this you need some large cardinals, and this is really because there is a theorem of Gittic and Magitor that you can force with large cardinals that this cofinality will be, for example, aleph omega plus 2, for example. You can take it omega plus 4, any gamma smaller than aleph 1, you want omega plus omega. Okay. So you first do this, and then you use the fact that when you use a CCC forcing notion, you actually cannot change these numbers by CCC. So all of these forcing notions that we heard, well, or some of them at least, in the first lecture, you can apply them now and you don't care about these guys. They will remain fixed. They will remain the same size. So here you add just dominating reals to make B equal D equal what you want. And then this will remain what it was before, and then you're done. So it's like a cookbook. You just took the recipe. You took the theorem and you applied classic method. So I put as an exercise, why did I use dominating reals and not Cohen reals? Everybody I told about, the first reaction was, okay, you can use also Cohen reals. Or can't you use also Cohen reals? So that's an exercise. Everyone who listened carefully to the first lecture should know the answer. Okay, so Medja can later check with people. Okay. Okay, so okay, but dominating is nice. Why you don't have to use Cohen when it doesn't work? Okay. Okay, so great. So I will finish with two open problems. I call them unavoidable problems. Unavoidable in the sense that if you study mathematics outside of set theory, you hit them. You hit them, and I showed you examples. So You cannot avoid them. You must solve them. You must solve them. I mean, us, set theorists, we must solve them. One of them is, okay, you can ask more general questions. What is this cofinality? For which kappa you can tell it in ZFC, etc. But in particular, because it's such a tame function, it tends to be kappa. Remember this SSH, Shellach-Strong hypothesis. Except for the case where kappa is countable cofinality, it is always, well, it tends to be kappa. It wants to be kappa. And we had some examples of this situation. So when is it the case? For which kappa can you prove in ZFC? Or not, I don't expect a full answer, but can you provide more examples than what the simple ones that I gave in this talk? When this happens, here are the known examples: omega power of cardinals, aleph n's, or this, or these cardinals. They all are fixed points of this function. So can you give more? Can you, in particular, find fixed points of this above this Shellach's point where it stops? I mean, can you extend the PCF theory, for example, beyond this cardinal? Just try to, there will be some distortion, but you will try to catch your tail. Go enough higher. Maybe the distortion will disappear, and the same theory will apply to cardinals below, I don't know, some other fixed point of the aleph function or something like that. So I think this may be a nice project because it will force you, so to speak, to learn PCF theory, and very likely something can be done. I don't know, unless there is a clear reason. You can first ask Shellach, but then you can also solve the problem. So maybe it's not a good idea. What?
For instance, the first cardinal fixed point, its power can be there's no bound.
There is this. So this is really, you say.
There's no bound for the first cardinal fixed point.
Mm-hmm.
Its power.
So that's the reason why everything stops there. And there is no chance, you think, I don't know, maybe some very mild hypothesis, something. I don't know. Okay, so maybe there is still hope to do something. I don't know. Okay. That's one problem. But also below this fixed point, I mean, these were very easy to produce, so probably there are deeper ones you can produce, or maybe you can prove that everything else is, may fail, so that would be also great. So, yeah. Second problem. That's somehow a problem that I find remarkable that it's still still open, at least as far as yesterday night. I don't know. Is it still open? Yeah, but it's open since the 70s, so it's amazing. First, I will tell the motivation. If you take, well, my motivation, why I think it is unavoidable for the general mathematician, or at least topologist. Let's take a billion metrizable groups, metric groups, A alpha. Now, you can talk about the direct sum of these groups. The topology here is defined such that each A beta is viewed as a subset of the direct sum, and this embedding makes it a subspace. So the embedding is continuous. The natural embedding. So with Gabor-Lukács, we observed that if you let kappa be the number of non-discrete A alphas in this direct sum, how many are non-discrete? Then the character of the direct sum, which is a natural construction, is this cofinality. Now, when you see it first, probably many of you saw it before, so it's not fair, but if you see it first, it looks obvious that you can actually compute it. What could it be? You know, the points of kappa is uncountable. They have no room, like in n. It's just the natural numbers. So it should be computable. But, so let us define f of kappa to be this cofinality. It turns out to be this cofinality also. Set theorists like this, so it's maybe more convenient. This is let's define for here, call it f of kappa. Then f of kappa is monotone and has these properties. Just for simple diagonalization, here just cardinality of n to the kappa. And the question is, when is it equal? It tends to be 2 to the kappa in a sense. So the question is, when is it equal really in ZFC? So it is known that if kappa is an omega power, so if you plug in kappa to the aleph 0, or lambda, let's say lambda is kappa to the aleph 0, then f of lambda is 2 to the lambda. The cofinality will be like the maximum value it could be. But except for this example, in ZFC. Are there more examples? I don't know. I didn't do extensive literature search. I posed the question in Math Overflow, still didn't see any references beyond. There were works by many, deep work by some people, but I didn't see examples of this answer, of this situation beyond. So in particular, it seems still open that whether the cofinality of n to the aleph 1 can be smaller than 2 to the aleph 1. This is open since the 1970s, works of Yech, Prikri. No, is it consistent? Now, I think Asaf told me it has nothing to do with large cardinals, or maybe. So I say, but I say even with large cardinals, is it consistent? So maybe it won't help you, but it won't hurt also. So yeah, maybe. So some things are known about it, but I don't know. How could it be that this is still open? I mean, my guess, I have a guess, because it is n there. As I said, it looks like a trivial object. I mean, it doesn't look like a theoretical object. It should be so easy that a student could solve it. But if you look at the results of Yech and Prikri, you see it's a deep object. It's a lot of set theory inside. So it should be settled. Maybe there is 1 week now in this conference. Maybe some of you can solve this, and I can return happy to my colleagues and tell them this is known. Okay, so thank you very much. That's the end of my lecture. Yes. Yes, this is because it was known what we did for compact sets. If you add that the compact sets are also metric spaces or metrizable spaces, then it was known. So our theorem for this case was known, and R is of this type. So that was known.
More question? So presumably the n appears here because you're only looking at a metric group or a non-metric group. And metric groups will have I to I0.
Yes, I suppose so.
More complicated objects.
Then you will get more complicated objects here, and in fact, I don't think we have theorems that actually give equality. This was very difficult to produce this theorem. It's not. So I believe that there are similar results. Definitely bounds. You can bet. You can get maybe less than or equal to, but and also here, objects with I don't know aleph 1 to the aleph 2, etc. Somehow they go the wrong direction. Maybe the smaller one is here, but also 2 to the kappa is like that. So that's fair enough. They were also studied by set theorists. I think everyone who studied, most of those who studied omega to the kappa also studied more general pairs. But this is sort of the most elemental, the most simple, let's say this one, that is still open, I would say. It's like, so I think it's the most intriguing question. Maybe. But if you can, I don't know, solve this question for aleph 1, I don't know, inaccessible, or instead of aleph 1, I mean, you put some kappa inaccessible or something, it would still be nice. I mean,
no, if kappa is strong inaccessible, then you have this power.
Equality?
Yeah. You have kappa to the aleph 0 is equal to alpha.
Oh, I see. Yes. Sorry. So you need something without that. Yeah. That's a very good result, by the way, this kappa to the aleph 0. I don't know who to attribute. I saw it in a paper of Hathaway, but he says that it's folklore or something. Maybe folklore.
Any other questions? Yes.
You mean the distinct treatment of this stuff? There is a paper by Yech and Prikri, I think. Yes. So if you search, I don't know if they have many papers together, but they can. 70s, I think, something like, or maybe I don't know. Yech worked a lot. You can look at Yech's book. There is a short discussion of this thing, this object, the cofinality of, and probably you can find all the relevant references there.